Okay, so let me start you off with kind of an example here. So what we're going to talk about today is differentials, linear approximations. They're kind of synonymous. So I've called up Desmos, which you all said you've all looked at. This is the function sine of 1 over x. Everybody knows what sine x looks like, right? It's just a wave, right? And the waves are kind of equally spaced. Sine of 1 over x kind of reverses both ways. As x goes to infinity, this goes to 0, right? So it's flat. So this is just one big wave here. And then actually, between any positive number and 0, this function crosses the x-axis infinitely often. No matter how close you are to 0, still it crosses infinitely often. Really weird, right? Actually, as hard as this is to graph, this thing actually does a reasonable job to it. Well, here's the point of what I'm trying to get. Let's blow this up. Let's get in closer. As you get in closer, you see that you can see there's peaks at the top of these waves, right? And the waves are getting closer and closer together. Well, let's just pick any one. Let's just pick, I'm going to try to center in on this top of the wave here. Let's get closer to it. This is the top of the wave. Now it looks kind of pointy at a distance, but as I get closer and closer to the top of this wave, closer, 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 what does it start looking more and more like? What does that almost look like when you get real close? Despite the fact that when you stand back and look, it almost looks at the distance like a point. Here it's flattened out. And if I go in closer and closer and closer, then it looks like a line, right? So if you were a small enough little ant, see that was the top of a pretty sharp little thing, but here, if we're on a small enough scale, it looks like a line, right? Well, let's kind of blow back out and see how, at the perspective we were before, it doesn't look like a line anymore, does it? So even a function like this, if you get close enough at almost every point, it'll look like a line. On the other hand, if you look at this function here, let's go up more. Now, of course, if you get close to a point right here, it looks like a line. In fact, locally, that piece right there is a line. But if you try to zoom in on where the pointy place is, right at 0, 0, no matter what scale you're on, no matter how close you get, it still doesn't look like a line. It looks like it's a sharp corner. Anybody tell me what's the difference between what happens to this function right at 0, 0 and what happened to the sine 1 over x one that we looked at earlier? What's different right here at 0, 0? It's different about the top of that wave on the side. Was it? That's right. The derivative, that's exactly right. The derivative at 0, 0 here doesn't exist. It's too sharp, it's pointy. You could do the same thing with something like x to the 2/3 power when you have the cusp or whatever. On the other hand, sine of 1 over x, top of that wave, on a small enough scale, it's round if you get small enough. And what we're going to do is we're going to look today at what we call differentials and linear approximations. So, now, this sounds like two different things, differentials and linear approximation. Actually, what it is two words for the same thing. And it's a slightly different perspective, but basically, here's what this is. What this is if have y equals f of x and f of x is differentiable on an interval containing a, then the linear approximation to y equals f of x is it's just given by the value of the function at point A. It's derivative of A, that's all we need differential on that interval A. Say. Anybody recognize this? What this f of A plus f of A. So it is just all this is fancy words. All this is a tangent to y equals f of x at the point A. Because recall well, what do you need to get a tangent line? You need two pieces of data. You need a point, there you go, and you need a slope. And what tool do we use to get the slope of the tangent line? Just the derivative. So if I would figure out the tangent line, I would put y minus f of a is equal to f prime of a. There's a slope of the tangent line. That's the point slope form of a line. There's your slope, and your point is a, f of a, and so y, I will solve for y. This, and we just call this L of x. This is called the linearization. Sometimes we call this linearization, or the linear, or a linear approximation function. The idea is you just use the tangent. That's it. Very simple, right? So suppose we have some function here, and it might be fairly complicated. And suppose that we know exactly what the value of the function is here. And I want to know how this function behaves in the neighborhood. And you might say, well, you've got the function, here it is, it's up there in black, and it's certainly is. But like I said, this might be a polynomial or something with crazy logs in it or something that's hard to compute. Plugging in for that kind of thing can sometimes be computationally inaccessible. Whereas plugging in for a line, all you do is plug in your x, subtract a number, multiply by a number. There you go. Much easier to do. So the idea behind this is you use the tangent line to approximate the function itself. Now, is this red line exactly the same as the function? Well, only right at this point, right? Well, would you agree that on a small enough interval, this line is very close to what the function is, right? And the line it's much easier to wrap your head around and do computations with than perhaps the function itself. Maybe this is something that measures how the economy is going to do, or, how likely the Earth is to get ripped apart by a black hole is growing. You want to understand what's going on here. You want to understand around this, and this thing gives you an approximation. Now, you might ask yourself, well, how good is this approximation? And the answer to that is that it depends. What about this? Here. And let's suppose that I do a tangent line approximation here at, say, a. Now, the idea is this linearization, this tangent line, it's not exactly a function, but I can approximate it, get numerical values close to this point, right? How good is it? Well, one thing that I can tell you is because of this, the way this function is behaving, it's a lot more accurate for a longer time, if you will, on the right side than on the left, right? It's okay to let for a little while, but after a short period of time, it diverges pretty badly, right? In fact, right here, the approximation is telling you that you've got a negative value, and look, it's very, very positive, right? On the other hand, over here, the reasonableness of the approximation seems to sort of last longer. You may explain what is it that's different about the black function here that makes it better, say, on the right as opposed to on the left? It's more curvy here, isn't it? So can you quantify that? Let me ask you. If you move just a little unit here, what's happening to the slopes of the tangent lines? Move into some where it starts to pull away. The change of the slope of the tangent line is changing pretty fast. And what is the change in the slope of the tangent? So the slope of the tangent line is the derivative, and the change in that is the second derivative. Notice right here, the change in the slope of the tangent line is pretty rapid. What happens to the tangent lines here? They're changing, they're increasing, but sort of at a slower rate. And that's why, so the tangent lines here haven't changed much from the original tangent line. And that's why it stays good. Whereas as you move here, the tangent line is moving away from what the original slope of the tangent line was pretty rapidly. Right, okay with that? And so it's actually sort of the second derivative that's telling you something about the curvature and why this works better here. That's kind of another neat application of the second derivative. Okay, let me give you an example here. Let's do some numerical. fine. But it has some square root, two square root. Can somebody ballpark these for me about one? What number do you suppose is to be close to? Yeah, it would be 11 point something, because, so how did you know that? Square root of 144 is 12, and that's an estimate here. I would expect this to be a little bit less than 12 and make this a little bit more. So what you used, Ryan, was you used this. Said square root of x. And you said, I know this. When x is equal to 4. Right, agree? So here's my function, the square root of that. I want to know, estimate f of 150 and f of 152. That's what I want to do. And I know so let's find. So my prescription for this is to find two f of x is x to the 1/2 at the point 140. And I'm going to use that to try to figure this out. By the way, here's kind of a picture of what we do. Square root of x is something like this. It's way out here. This is 144, and this is the point 144. What? And basically what you want to do is find this 150 and 142. Now the square root function does flatten out pretty good. So basically what we're doing is we're using tangent line to estimate. Let's find the tangent. So in this case, and notice that f of x, 6 to 1/2, f prime of x is 1/2 of x to minus 1. So this comes to 12 plus, let's see, when I plug in 144 to this becomes 112 and 1/2. So this is 1.4. So this is actually 12 plus 124x minus 6. So I get 124x minus or plus 6. So if I want to estimate this. So I assume that f of 150, which is square root of 150, is approximately equal to L of 150, which is equal to 150 over 24 plus 6, which is 75 twelfths, 6, which is 147. So actually, this turns out this estimate that I get, see, it's going to be 12, and then 3/12, 12.25. And this vehicles, let's see if we get here. Yes, what I get on my calculator is 12.247. So pretty close, right? I mean, this little linearization, it allows me to do things in a fraction in my head, 12.25. It's pretty inaccessible just by finding the square root. F of 142, which is square root of 142, be approximately equal to L of 142, which is 142 over 24 plus 6. For that. And this is 71 twelfths plus 6, which is 143 over 12. So this is 12 minus a 12. Okay. So this comes to like 11.9. Yes, I get 11.916. So not too shabby for back the info calculation. Right. Let's try another one. By the way, let me ask you a question. Are these estimates too big or too small? Let me know. But you should know for a reason. Look at the picture. The tangent line sits on top of the curve. And the tangent line is what's telling me the white points. The red thing is what's giving me my estimates. The black thing is the true answer. Right? And since the red thing is on top of the black thing, it should be giving me something a little bit too big. How about this? Estimate tangent to there's something sort of wrong with this problem at the outset. What do I need to do? That's exactly right. I need to change the British ratings because remember our trig functions need to be ratings because you take the derivative of tangent, it's in degrees. It's weird. It's sec squared and you have this factor of like pi over 180. So recall 1 degree is equal to pi over 180 radians. So let's recalculate the problem. Estimate Okay. Just like before, can y'all think of something that's pretty close to 2 degrees, or 90 radians, where you actually, honest to goodness, know what the value of tangent is? 2 degrees is pretty close to 0 degrees, isn't it? Pi over 90 is pretty close to 0 radians. What's the tangent of 0? 0. And that's what we're going to do. So we're going to find Lx at 0, 0. Let's recall that if f of x is x, then f prime of x is secant squared x. So Lx is equal to f of a plus f prime of a, x prime the same, which in our case is f of 0 plus f prime of 0, x minus 0. Well, and f of 0 is 0, and f prime of 0 is 1. So L of x is equal to actually just x, because that's a 0, and that's a 1. So tangent of 2 degrees, which is tangent of pi over 90, is approximately equal to L pi over 90, which is pi over 90. Pi over 90 is about 1/30, a little bit bigger than that. Not much. But let's see how close we get here. So pi over 90 is about pi over 90 is about 0.349, 585. And tangent of pi over 90 is approximately equal to 0.3 0.34926. So notice that this agrees until within decimal points. Okay, any questions on that? Okay, now I'm going to do the same thing, a different approach. So you might say, well, Jim, why are you doing this? Why are you messing with their heads? Tangent all the time it does. I'm going to show you another perspective. So this is essentially the same thing, but this approach called differentials allows us to do things like compute percentage error, things like that, more easily. How many of you have ever had chemistry? How many of you have done experiments in the lab where you have to get some kind of result, and then they ask you to figure out what your percentage error? You ever done those kind of things? Okay, you get this result, what your percentage error. This will allow us to do that kind of thing as well. And I'll give you some problems here that will put this in perspective. Again, this is just looking at the tangent line approximation from a different perspective. Suppose you have some function. And you know what the value is get this point here, A, F, and you know that. Now, what you do is you want to know what the value of the function is. A little later, or maybe a little sooner. My delta x could be negative. Maybe I won't know what it's like on the other side. Here is the value of the function. It is what it is. This is the point A plus a little change in x, F. And this may be hard to compute. So here's kind of the same parallel. Show you what I mean. Let's suppose that x is x plus minus 2 squared. Here's a value right here. F of 1 is what? I think so. 14, 12, 17. Everybody agree with that? What's that? Yeah, good luck, right? I mean, who wants to take the power of this? This is not something you're gonna be able to do by hand. Right? Now, we'll come back and see if we can get the best of this. So my increase. So what we're doing with differentials is we're figuring out how much the function changes. This is what I call delta y. What is delta y? It is the actual, honest to goodness change in the y coordinate as I go from A to A plus delta x, right? You change by delta x, y, and you increase by delta y, right? I'm a lazy creature. This may be hard, like in this problem. For this problem, by the way, what is my delta x? How much did I change by x? 0.13. Everybody agree with that? I increased my x by 0.13. How much did I increase my y? That's a little tougher. So let me show you something easy. Take the tangent line. And we're going to call this dy. So here's my notation. I use change in x and dx synonymously in this notation. It's just a change in x. They're the same. Delta x dx. These are just different names. Tomato and tomato. Dy and delta y are different. Dy is f prime of x dx. And I keep this notation because it will be useful to mnemonic device later, not only in this course, but in as well. Here's kind of a this is an easy way to kind of remember this, right? Although this is kind of sloppy and me, instructor, but this is kind of a good mnemonic device. D by dx is the derivative. This thing right here is called differential, and it's used to compute this. And what does this f prime tell you? It's the slope of the tangent. So what this equation right here says is, when you take the slope of this line, slope of the red line, times how much you change in x, that'll give you your dy. Right? That is, multiply how far you go by the slope, and that tells you how much you rise. Right? Rise over run, the slope of the tangent. Now, the dy is usually much easier to compute than delta y. Delta y is the honest to goodness. It's real life. dy is our estimate. So for example, if we continue this example here, estimate this. dy, which is f prime. So our dy in this case is f prime of x Everybody agree with my derivative? Let's see if I do. Now to estimate this change in y by using dy, I need to know two things. I need to know x and dx. I need to be able to plug in numbers for this. What do you suppose is the appropriate number for x? That would be the dx. That's how much you're changing. What would the x be? What's sort of your base need? 1. Start at 1, you change positive 1 to 3 for that. Let's see. That's going to be 5, and 52 is 57, minus 4 is 53, times. So that's going to be like 0.53, 0.5. That's, yeah, 0.6. Anyway, so let's see how good we are. I'm not convinced we're actually going to be too good on this one. Let's see if we can criticize. That's the case. 53 times 1.3. This estimates change plus. How do we find the real change? Even on a calculator, this is obnoxious. The actual delta y is f of 1.13 minus f1, which is f of 1.13 minus 17. We can figure that out. Let me see if I can figure f 1.13. So I get, I did this right, it's 25.484. 79 minus 17. So this is approximately equal to 8.48479. So whether or not this is a good estimate or not is a matter of opinion. Scale, I guess. It estimated that we jumped by this much. We actually jumped by this. I'm not surprised that it's a little off. Let's actually try this. Oh, yeah. Let's try this again on the scale. So our estimate missed by what? We'll say 1.5, something like that. How about this? Not this, right? This is what? 100,000 plus 13 times 10,000 minus oops, it's a lot more. That's not 10. Actually, I think 10 will probably do just fine. That'll make it easier on us. Yeah, 100 to be out of control. Let's try this again. It's 10 to the 5. This is 100,000. This is 13 times 10,000 minus 200 plus 5. So that's 230,000 minus 200. So that's 200. I agree. Right, 200 that, which you get 230. Now, let's do the same thing. All right, nobody wants to do this, right? Plug it in, although we will check it. Let's estimate the change now. Lucky us, we have the same derivative, right? This time, what's my base? What's my change? Good. So this time, my dy, my estimate is that's 50,000 plus 52,000 minus 40 times 0.13. So this is 2 196. Times 0.13. So what do we get here? 1.196 times 3. So I get an estimated change of 13,254.8. Is that right? So now what do I get for the actual change function? Well, f of 10.13, let's persevere, 10.13 plus 13 times 10.3. minus 2 squared pi. So I get this is like 243, 363. 16, 9, and so my difference is 243, 363.9437 minus 229,805 comes to be 13, 558. So, oh dear. See, I only missed the other one by, what, 1.5. Now I missed by, goodness, I missed by like a couple of hundred. Is that worse? Fourth things, right. Fourth thing is very important. This is actually a pretty reasonable estimate, given the size, or given the size of the output of the function. So let me give you an example. I looked this up before class today. I'm a curious fellow. The radius of Jupiter is 43,441 miles. You know, when I read this, I thought, boy, that's a lot of significant digits for something that Jupiter, its closest point, is roughly 400 million miles away, right? Seems like a pretty tight measurement. Let me cut this down here. We'll say, so for our purposes, radius of Jupiter is 43,450 miles. We'll say an error plus or minus 10. Let's suppose, just for giggles, let's suppose that we can measure the radius of Jupiter. And we say it's 43,450 miles. And to account for this, I'll say it's got an error of plus or minus 10 miles. Right? So we're saying we measure the radius of Jupiter within 10 miles seems like a lot, right? I mean, I'm 10 miles away from home. It took me a long radius, right? So when I make my measurement of the radius of Jupiter, I'm not quite sure. Am I? It can be 10 miles more. It can be 10 miles less. So so here's my question. What is maximum error in using this figure? Volume. See, maybe I want to know something. Maybe I want to know what its surface area is. Maybe I want to know what its volume is. In this case, I want to know its volume. To measure the volume of Jupiter, I need to know something. I need to know its radius. In that measurement, whenever you're taking a scientific measurement, there is error involved. this error is going to flub up me using a formula to figure out the volume. And I want to know, hey, if I miss my measurement of Jupiter by say 10 miles, how much is that going to screw up my estimate for how big Jupiter is? Volume. I want to get to the bottom of this. So here's kind of the problem. And this shows sort of why. So here's Jupiter. And I measured this radius R. Now, I could have missed this by a little much. Maybe I missed the radius by that much. And if I did, Jupiter's actually fatter than I thought it was and has more volume. That'll give me an error. I could have measured it too small. Right? I want to figure out how much I missed the volume. Okay, so to make this problem work, the first thing I'm going to need is I'm going to need a volume of the sphere. Anybody know what the formula of the volume of the sphere is? I think it has to be cubed, right? Because think about the units. That's one place with the units that help you out. Just give this a right. Again, this is something you'll be able to draw from scratch when you're tonight. Okay, there's your volume. And what we want is right? We want to find how much changing R one way or the other changes the volume. Right? This is too freaking hard to compute. It's hard because what you have to do is compute the volume with R plus dr, keeping something out of variable mass, and R minus dr figured out. So here's the whole idea on differentials in this case. This, I'm going to use this approximation. This is approximately dV. And dV is the derivative of this dr. Everybody see how I got that? This is just like my dy is every time of x dx. My dV is the derivative here times dl. In this case, for our specific problem with Jupiter, what's my R? What's my base? What did I say that I measured base? This is, maybe I should take this off. This is just what I found on Google, right? And I use this as I want to use something around. This is my measurement, right? This is my base, 43,450. How about DR? How much can I change that? What's change? 10 miles either direction. So my dV is 4 pi 43,450 squared times 10 plus or minus, really. And this should be cubic miles. Just for giggles, let's see what we get. What do we got here? 43,450 squared times 4 pi 10. I get 2.3724. Well, which is, um, 7. So missing the radius by plus or minus 10 miles, I could miss the volume of the planet Jupiter by 237,240,000,000 cubic miles. That's a good estimate. Doesn't seem like it, does it? Let me, that's about foot, right? A cubic foot, probably 12 inches. A cubic foot is a box, about like that. Do I agree with that? What if I told you I could measure the volume of a basketball and miss by no more than a cubic foot? How many of you would be impressed with my mathematical prowess? Nobody, right? I mean, I could just say 1 cubic foot, and that's pretty close. What if I could tell you I could measure the volume of the galaxy and not miss by a cubic foot? That is a more impressive thing. Agree? So I don't know. Let's answer that question. How big is this? And actually, it turned out it's quite big. So those of you that have been subjected to chemistry, you remember computing percentage error when, what did you do? You took your theoretical minus experimental and you divided by theoretical, right? So what we have here, this is just my error. That's how much I'm estimating that I can miss this by. Over 237 billion cubic miles. Well, what's the relative error? It should be that. Theoretical minus experimental. Theoretical minus experimental is a change, right? I've got my theoretical volume of Jupiter from computing this. My experimental can be plus or minus the 10 miles, right? The difference between my theoretical measurement and what it actually is, well, that's the change in the measurement of the volume of Jupiter. Everybody okay with that? And there's my theoretical. I'm going to approximate this as dV over V, because after all, this is, I'm in the business of making this approximation. And instead of putting numbers in, I can make this a lot easier. dV, I've already figured this out. It is 4 pi r squared VR, and V is 4/3 pi r cubed. Notice no numbers here. It's actually easier without the numbers. Right, okay? The pi, there's a crazy amount of cancellation here. Pi's cancel, 2 powers of the R cancel, and 4's cancel, and I end up with 3 dr over R. This is my relative average. What is dr? Right, and I'll take this in absolute value, I'll just take 10. What's R? What's my theoretical measurement of Jupiter? So this number comes up to 3, about 43,000. And folks, that comes up to a pretty small number. So this is 30 divided by 43,450. This is about 0.00069. Or I remember in my old industry days, they always think of me like that in high school, percentage error. This is a 0.07% error. Multiplied by 100, which is percentage error. And I don't know about you all, but whenever I used to sit in labs, if I was ever under about a 20% error, I was happy with myself. My experiments never worked out very well. This error is, so even though it sounds like a big number, and it certainly is a big number, 237 billion miles, it is very minuscule compared to the size of Jupiter. So that measurement is, I mean, and if you think about it, good luck measuring, radius of Jupiter from this distance within 2 miles. Right, that would, you'd have to do some significant work. Do you know the actual percentage? Oh, so if you could, so what you could do, if you wanted to do this, figure out what the actual thing. So yeah, you're right. This is the real relative error. This is our estimate, right? You could go through and do this sort of long, but it's long and it won't be very much different. Here's another kind of practical application problem for this. These were always fun problems to do. When I was in North Dakota, it's like silos and ice. But of course, here in the South, we get really windy winters, but oftentimes we do get bad winter weather once it's on ice. So, example, a farmer has a silo with a conical roof of base radius 30 feet and height 15. A nice one is coats solid roof uniformly with a 1 inch shell ice. If water weighs 62.5 pounds per cubic foot, estimate weight of ice on roof. Is, over or under. Also expect. So here's the deal. You got this farmer. And he's got a 30-foot diameter silo. And he's got this conical roof on it. And the silo, 30 this way, 15. Right. Along comes this ice storm and it coats his roof 1 inch thick with ice. He wants to know how much that ice is going to weigh. Is it going to compromise his roof? It's the thing of the house. Right. Okay, first thing is let me remind you of this. The volume of a cone is 1/3 the base, which in this case is a circle. Height. Now, it's very tempting to plug in numbers for this, but don't, because this problem is dynamic. Is the farmer's roof always 15 tall? Well, roof, yes, but when you start adding ice, it's going to be bigger. So actually, the dimensions of that cone can sit on top of the silo and change because you're sticking ice on it, you're making it grow. Agree? But there is one thing that we can take away from this. When you add ice to this, I did say it's uniform, so it should be proportionally. Let's call this R. Now R might be a little bit bigger than 30 because now you got a little bit of ice on it. And what's the height? It should be a little bit bigger too, but if you put the ice on the uniform one, it should be 1/2 R. Right? It should preserve this relationship. That is, the radius is twice the height. You're adding uniform. So for the farmer, he's got this growing roof. Radius R, as ice is being added, and height 1/2 R. Basically. So the volume of this dude's silo is 1/3 pi R squared times the height, which is 1/2 R. So I get the volume is actually 1/6 pi R cubed. Everybody okay with that? We see the change when it goes from 30 feet plus 1 inch. Right? So what are we going to do? We're going to be lazy and estimate this. Now, for this particular problem, somebody tell me what my DV is. What is DV? for this problem. Where are you getting the one part? Sitting in one half. So yeah, one half. R to what power? And what do we tag on to this? Okay with you? Okay, make this work. I need numbers. What is R? Perfect. Great. What is DR? 1 inch, right? Let's follow that. Yeah, it's the wrong unit. So let's turn this shallow. This is 112. So let's see what we get. Change in volume. Change in volume of this guy's roof, which is the amount of ice you've added to it. You went from roof with nothing, roof with some volume of ice, is approximately equal to this differential estimate, which is 1/2 pi, 30 feet squared, comes to 112. And this comes to 924. It's 225. So this comes to about 235. Approximately. 235.62. Now the question was, how much does that weigh? That's how many cubic feet of ice. So weight should be 235.62 cubic feet by 62.5 pounds cubic foot. And this is 14,726. Basically, it's got about almost 7.5 tons of ice on this roof. Does that surprise you? Water is heavy, right? That's why ice is dangerous. That's why the power lines. Because I mean, you could do that computation. I mean, just imagine that you add the thickness, take like a standard electrical wire, right? Imagine an ice storm uniformly coats that with, it's icy goodness, right? Figure out how much that weighs. It might surprise you. That's why power goes off when you get an ice storm. Last question. So we estimate this guy's got, 7 tons and some change of ice on his silo roof. This is after all. Is it too big? Overestimated or underestimated? This is pictorial. Here's our function. This was the function that we used to estimate, right? Now, this doesn't have to be perfect, but I do know that a cubic looks something like that. I don't care about it on the other side. I care about positive value of R, right? What did we do? We went from 30 feet to, not to scale, 30 feet plus 1 inch, right? Right. This is the actual change in the volume. Did we overestimate it or underestimate? What all of these approximations do is use the tangent. We underestimate. So it's actually heavier. Probably not by much because this curve is actually pretty steep. And for a small change like that, it's almost like a line. But nonetheless, this estimate is probably too conservative. Any questions? Okay, so this is what I want to talk about. Go over this. These are very neat applied problems, even though some of them at first seem silly, like, oh, you know, estimate the change of f of x is x to the 9 plus x to the 8 plus 7 from, you know, 2 to 2.5. That does seem silly, but you can see how this lends itself to nice applications, right? Errors in mass, errors in volume, how heavy some poor guy's roof is about to collapse. So we have some time for the quiz. So I thought that we could probably talk about one or two of the problems from last time. What was the problem last time? We had the circle and the instructions were to cut a wedge. Sorry. Hold on. What is the maximum volume of the cup in terms of radius? Or R is radius of the circle. The idea behind the problem is because some wedge out of it. The back, and you fold that up into a cup. By connecting the red pieces, kind of pulling them together. Quite understand? Okay. First thing to do is to draw a picture. Here's the cup. It can be. And I did give you the, during the quiz, I did give you the formula for volume. What should I label them? Okay. I need the radius of the cup. I need its height if I'm going to. That's. I need the radius and the height to be able to get volume. So the volume of my cup is 1/3 I x squared h. And that was it. And we want to maximize this volume, right? What's one problem that just leaps out at you right here? too many variables, right? It's how one prints. Actually, I left something off my picture. My picture's a little bit naked, but something else that if I make the right observation, put on is all worth noticing. We'll have to use that in a moment. But here's my question. You know what the hypotenuse is? Ah, very good. The hypotenuse down here is R. It's the radius. It's the radius of the original paper circle. Right? That's very important. Everybody can see that? We fold that cup up, so we glue this together. This length right here, going down the cone, is R. Everybody okay with that? That's key. We also know that x squared plus h squared r squared. And this equation right here is what allows me to get rid of one of the variables. Now, let me ask you this. We got two choices. We can solve for x, plug in. We can solve for h, plug in. Which one's better? X, y, x. Yeah, that's right. It's already squared. As a challenge to you, when you go home, do it both ways, right? In fact, if you're trying to get good at this, get in good physical shape to do these kind of problems, do it both ways. You can do this with h, but it might make you cuss a little bit because you'll have some square roots when you take derivatives, which is obnoxious. So what I'm going to do is, since x is only in there in the square form, I'm going to do that. Plug in. So what I get is I get a new improved volume that has only one variable. I got that. And I'll write this another way too. This is 1/3 pi r squared h minus 1/3 pi h. And that's what I get multiplying this out. And I just want to do that because it's easier to take it. What should we do at this point? Well, let's not get ahead of ourselves. Remember, one of the things that you should always do in these kind of problems is ask yourself, what's the playground? What are the values for h that are appropriate? How small could h be? It could be 0. If you don't cut anything at all, just let that paper circle set there, it ain't gonna hold anything. You can pour water out of a water cooler and feel like an idiot, but nonetheless, do it. How big? Sort of limits to R, doesn't it? And there's no reason it can't be R, really. And I'm digging this because it's continuous function on the closed. Derivative, d prime is 1/3 pi r squared minus pi h squared. Now we're looking for critical numbers in this range. This is never undefined, so I'm going to set this equal to 0. I'm going to get pi h squared is 1/3 r squared. Pi's cancel. We get h is r over the square root of 3. Actually, plus or minus r over the square root of 3. But why do I not care about the negative? Right, because the negative's not in. Is this in my range? Is this an acceptable value? Yes, because what are you doing? You're taking r and you're dividing by a number that is bigger than one, so it's gonna be a little less than R, and it's certainly positive. So this is kosher, this is a good. So I'm digging on this because all I'm gonna do is check. The endpoints have got to give me 0. Notice that B of 0, 0, putting in R equals 0 gives, not R equals 0, H equals 0 equals 0. Plugging in R also gives me 0. And so if I get anything that's positive, plugging in R over square root of 3, that will be minus. And what do I get here? I have 1/3 pi R squared minus 1/3 R squared. That's what you get when you square that thing. Times R over radical. So what do I get? 399 radical 3. There's your maximum bar. Let's do one more. With. How about the sausage? Um, and I think also this described. So if you have a triangle with two sides A, you can certainly do something like this. I'm trying to make it the same way. Do something like this, right? I mean, imagine it's like a pair of scissors that I can open. I can get it almost flat. I can get it almost somewhere in the middle. It seems like the area would be as big as possible, right? Let's see what happens. So let's label this. This is A. It's supposed to be outside space. What else? Yes. We'll call this bottom B. What else? Do that. Well, what do you need to get the area of a triangle? You need its base and what else? Okay, so maybe I should look for that too, right? Let's call this type H. Now notice A is always the same, but B and H can vary. Right? Area of this triangle. Somebody give me a pointer for the area of this triangle. Good. 1/2 BH. There we go. That's what we're trying to make as big as possible. What's my problem? Too many variables, so I need to get rid of one of them, probably. Need equation. Involving B and H. That's 1/2 B, right? So does anybody see the equation involving H and B? This is right triangle, very good. So we've got the Pythagoras theorem. So this is 1/2 B 1 squared plus H squared. So I get 1/4 B squared plus H squared. And actually, you know what I'm gonna do? You don't have to do this, but I'm going to get this B squared plus 4H squared or A squared. Just because I don't feel like I'm mucking around. Make it a little easier for me. And so I get B squared is 4 A squared minus H squared. So B is 2. Okay, so after all this work, I've got a new improved formula for my A. A 1/2 BH, which is H times the square root of H squared minus H. For A, H squared minus H squared. There we go. What should we do now? Well, let's look at what our playground. My H here, let me look at my picture. How small could H be? It can be 0. Stupidest triangle in the world. It's just a flat line. With 2A, but there's nothing stops me in front of this. How big? No, because you're limited by these A's. They never get any bigger. How big are they? Well, think about what happens. As H gets taller and taller, the A's fold in, it's going to be A. Yeah. Now, let's take a derivative. Take this derivative. Remember, our variable here is H. You've got to do a product rule, don't we? So this is going to be 1 times A squared minus H squared 1/2 plus H times 1/2 here 1/2 A squared minus H squared minus 1/2 times minus 2H. Now let's pull out an H squared minus H squared to the negative 1. This is going to leave A squared minus H squared 1 power. And when I pull this out, this is going to be what, minus H squared. That's going to be 1/2 H. So I get this. Is and I get a slew of critical numbers here. Let's I get H equals A, negative A over the square root of 2 minus A over the square root of 2. Plus or minus A comes from this, plus or minus A to the square root. Which ones can we eliminate, if any? The negative ones are right out. They don't belong in our problem because these two, however, are kosher. A, I got a critical number that corresponds to an endpoint, so that'll save you some money. And this one again, A divided by square root of 2 is A divided by some number of root of 1. It's in this range. So let's see what happens. A of 0, A of A. Well, when I plug in 0 for H, I get 0. When I plug in A for H, I get 0. So again, all I need is for this to not be 0. And what do I get? I get A from the square root of 2 times A squared minus A squared from 2 half, which is A over bracket 2 times A over bracket 2, which is 1 half. So if you want to describe the triangle, by the way, what this means is your H, A here, A, and your H is A divided by the square root of 2, which means that your bottom here is A times radical. So in other words, this is a 45, 45. Okay, any questions? Any questions? Okay, keep working on these problems. Previous section, like I said, the next moves is going to be important in this section too. So be sure you keep working on that.